Hey guys, welcome to another session on math for data sciences. So, in our previous session, we looked at something called variable encoding, which was a concept to basically convert the categorical variable in some kind of a numerical form so that they are able to be recognized by the machine learning algorithms. Because machine learning algorithms in general cannot work with the categorical data directly like colors, and therefore we do variable encoding for such variables and convert them into their numerical form, which then goes as an input features to these machine learning models. We looked at a couple of ways to do so for nominal variables, where we looked at label encoding and one hot encoding. And we normally use one hot encoding for nominal variables, where we create a new feature for each value of the variable, so color in this case. But we normally create n minus 1 dummy variables instead of n variables, because there's a repetition in one of the column, and we don't need to add an extra feature. Therefore, just like we saw in this particular example, for three colors we were able to get two different columns, which was the blue column and the green column, and using these two columns we were able to still differentiate between the three distinct values of the variable color. Therefore, we need n minus 1 dummy variables for n possible categories of a categorical variable. Next, we looked at ordinal data, and for ordinal data or ordinal kind of variables, we have something called ordinal encoding, where we simply assign a value from 1 to however number of categories are there. We assign the values in the same order so that the machine learning model is able to take into consideration the order between the different possible values of the ordinal variables as well. Next, we in this particular session, we would be looking at something called measures of central tendency in a variable data. So what this does is basically this gives an indication of how basically what is a typical value. So let us say this is a typical value of a variable, or one can also say this is like a central value of the variable. So this is actually very similar concept to what we were while we were studying the expected value of different distributions or the average value. So this can also be said as an average or expected value of the variable. Now we'll be looking at many ways here how a particular measure, how a central tendency of a particular value set of values could be computed. So the first one we would be looking at is called mean or arithmetic mean. So this is the very common measure of central tendency, and all of us already know how to calculate it. So just a simple example. Let us say we have a set of 5 values here: 5, 8, 12, 20 and 25. Now to calculate the arithmetic mean, we simply calculate the ratio of the sum of all values with the total number of values. Now the sum of all values, 5 plus 8 till 25 divided by 5, this comes out to be 70 by 5 equal to 40. Therefore, 14 is the arithmetic mean value of this particular data set. Now, one thing to note, whenever we are calculating a measure of central tendency, we should take into consideration whether the set of values has any extreme values or outliers in their data or not. So outliers are those values which are like an exception to those particular set of values. So we saw, if you remember, we saw the outliers detection method called Tukey criteria when we were looking at the quartiles. So if you remember, the outlier was defined as a value which is less than Q1 minus 1.5 times the interquartile range, or x greater than Q3 plus 1.5 IQR. So this basically suggests that if the value is way too low or if the value is way too high, that particular value is called an outlier. Now let us say we take an example. We take a set of values here, 5, 8, 12, 20, and let us say the last value here is 200. Now in this particular case, if we calculate the mean, we once again sum up the values. So 5 plus 8, 13, plus 12, 25, plus 20, 45, plus 200, 245, divided by 5. This comes out to be 49. Now this 49 value, although is the arithmetic mean of these set of values, it clearly doesn't represent a typical value in this particular data set. The reason being, most of the values are actually way lower than this arithmetic mean value, and we can see that there are 4 out of 5 values which are way less than 49. Therefore this doesn't look good as a typical value for this particular data set. So what this shows here is that arithmetic mean as a measure of central tendency is sensitive to outlier values. So arithmetic mean is sensitive to outlier values because it gives equal weightage to all the values in because we are adding all the values in the numerator and we are giving equal weightage to each value in the numerator. Therefore it is sensitive to the outlier values because it gives equally importance to each of the value in the data. So to counter this, what we do is we look at the second measure of central tendency, which is called median. Now median is nothing but the middle value of a data set. Once we arrange the values in an ascending order. So if we arrange the values from smallest to largest and then we look at the value which comes in the middle, that will be considered the median of a data set. Now let us look at the same example. So 5, 8, 12, 20. 5, 8, 12, 20 and 25. Here since the middle value is clearly 12, therefore median is 12. Now let us look at another example with outlier. So 5, 8, 12, 20, let's say 200, and the median still remains 12. Therefore even though we have an extreme value here, the median is unaffected by that extreme value, and therefore this is median is good for cases or for data with outliers. So if one has to decide which measure of central tendency could be a better value to be kept, we would want to have a median used instead of the arithmetic mean whenever there are outliers or whenever the data is skewed. So if you remember when we were looking at the skewed distributions in our probability distributions sessions, we had data something like this, which was a positive skewed or a right tail distribution. Now if you look in on the graph here, these are the typical values here. So this particular set of values could be said a typical values for this particular variable, but then there are some values here and these could be called the outliers. So whenever we have a skewed kind of a distribution, there will be outliers in that kind of a data, and therefore one should always use the median instead of arithmetic mean to represent the measure of central tendency for that particular data. So these are the first two measures of central tendency which we have looked at here. Now next, coming to non-numerical kind of a data. Now let's say we have a data where we have colors. So we have values, let's say G for green, so we have G, then we have R, then we have G again, then for blue we use B, R is red, so we have B, then we G, and then R, and then again B. Now, since this is a categorical variable, which is a non-numerical variable, it becomes impossible to either arrange them in a particular ascending order. Therefore, we cannot calculate median because we cannot say one color is greater than the other. And also, as the arithmetic operations cannot be done, we cannot really sum up these values to calculate the arithmetic mean. So, both the mean and median cannot be computed in this particular case. So therefore we look at something called the mode of a distribution. This is the third measure of central tendency, mode of the distribution, which is the most frequent value in the distribution. So in this particular case, if we count each color, we see that G is coming 4 times, R is coming 3 times, and B is coming 2 times. Therefore, mode of the distribution would be given as green in this particular case. Now, although we are showing here that mode is calculated for categorical variables, we can also actually have certain numerical data where we are calculating the mode of that data. But it won't make sense if the number of if the variable is continuous and there are too many distinct values for that variable. In that case, the mode will not make sense because there could be all the values which are only coming once, and therefore it will become impossible to get the mode. It will be like a multimodal distribution where there are too many modes, since they are occurring, all of them are occurring at the same number of frequency. Now, one more thing before moving ahead, we saw median calculation as the middle value of the data, but what if, now let us say we take another example. Let us say we have 5, 8, 12, 13, 16 and 20. So there are 6 values here. Now, since there are even number of values, how can we calculate the median of such a data? Because there is no true middle value in this particular case. So in that case, what we do is we take the middle 2 values. So in this case, that would be the third and the fourth value, and we calculate the mean of these 2 values to get the median. So whenever you have even number of values in the data set, the median is calculated as the mean of the middle 2 values, and therefore in this case it would be calculated as 12 plus 13 divided by 2, which is 12.5. So this will be the median of the distribution. Now moving ahead, we would be looking at something called a geometric mean of a set of values. So for this, let us say we take a particular example from the finance application, specifically financial mathematics. So let us say we have a certain investment at time 0 and it is valued at 100. Then we get a, so let us say we have a return column here. Now we make a 10% return till year 1, and therefore the investment amount becomes, sorry, it becomes 110 because 10% is added to $100, and therefore it becomes 110. So let us say this is investment. Now at t equal to 2, let us say we make another 20%. 20% is specifically made in year 2, and therefore the value here becomes 110 into 1.2, which becomes, so 20% of 110 is 22, and 110 plus 22 is 132. So the investment value total becomes 132. Now if one wants to calculate what is the average return for the investment, so one can say that we can find the arithmetic mean, which was the first measure of central tendency we looked at, and we can calculate the arithmetic mean for the 2-year period as 15%, since we got 10% in the first year and 20% in the second year. But now if we had got 15% in each of the year, then ideally our $100 initially should have been 100 into 1.15 into 1.15, and this will not really come out to be the exact amount. So it comes out to 132.25, which is not equal to 132. So clearly this doesn't represent a true measure of central tendency in this particular case, since the total return should be actually less than 15%, given the fact that we are having the final investment value as 132 instead of 132.25, which we would have got if we would have had 15% in each of the 2 years. So to tackle this, we use something called a geometric mean, and how we calculate it is, instead of so we can assume, let us say the geometric mean value is x. So after each of the year we are getting a return of x. Therefore after 2 years we have 1 plus x whole square as the total return from $100. Now this should be equal to 132, because that is the true investment value at the end of a 2-year period. Now this becomes 1 plus x whole square, and 132 upon 100, which is 1.32. Therefore 1 plus x is nothing but square root of 1.32, and x is calculated as 1.32 square root minus 1, and this comes out to be 1.1489 minus 1, which is 0.1489 or 14.89%. So this is the true geometric mean return for the given 2-year period, which means that if we get a return of 14.89% in each of these 2 periods, then we would have come up with the final investment value as 132 instead of 132.25, which we were getting when we were using the arithmetic mean. And so this was one example where geometric mean could be used, but normally whenever we encounter rates or ratios, just like we had here, so we had rate like in terms of percentage return, and actually we had ratios as well. If you look at it closely, we are actually having 132 divided by 100 as the final investment value per dollar invested. In these particular cases we use geometric mean, but normally you will not see many examples. This is the most used example in financial applications, where you will be using geometric mean when you are asked to calculate the total effective rate of return, or the geometric mean return, or it is also called the compounded mean return, because you are compounding the total return by multiplying the return for each period here, 1 plus x into 1 plus x. So this is also called the compounded mean return for the given example. So this is how you calculate the geometric mean, which is also the 4th measure of central tendency, which we have looked at here. Next, let us say we have another example here, and this particular measure of central tendency which we'll be looking at here is called the harmonic mean. Now for this, let us say we take an example from speed, distance, time. So let us say there's a car which goes from point A to point B, and the total distance between A and B is D. So the car goes from point A to point B with a speed of, let us say the speed is V1, and then once it reaches point B, it again from point B to point A, it again goes from point B to point A, but this time the speed of the car was V2. So basically we are traveling a total distance of D plus D once from A to B and then from B to A, and in our initial first cycle our speed was V1, while on the second cycle it was V2. Now we have to calculate average speed for the whole journey. Okay, so now to calculate the average speed of the whole journey, one could argue that we can again calculate the arithmetic mean. So the arithmetic mean is calculated as v1 plus v2 upon 2, but this is will not be the actual actual mean speed, and we'll see why it is not correct. So let us say we want to compute the total time of travel in the whole journey. So we have time calculated as distance upon speed. So obviously time is calculated as distance upon speed, and once we go from A to B, the time t1 is given as d upon v1, and once we go from B to A, the time t2 is given as d upon v2. So in both cases the distance is the same, but since the speeds were different, therefore times would also be different. Now if we add both the times, we get d upon v1 plus d upon v2. Now if we use this particular mean speed, the arithmetic mean speed, which we calculated as v1 plus v2 upon 2, and we have this particular total time already, then we know that if we multiply speed into the total time, we should get the total distance as 2d, because that was the total distance traveled. So let us say we try to do that. So we get v1 plus v2 upon 2 multiplied by d upon v1 plus d upon v2. Now this comes out to be v1 plus v2 upon 2. Now we take the common denominator v1 v2, and we can bring d outside here, and we are left with v1 plus v2. So this becomes d upon 2 v1 plus v2 whole square upon v1 v2, which is clearly not equal to 2d. Since we multiplied the total time with the total average velocity, average speed, and we are not getting the correct distance which was traveled, which was 2d, therefore this is not a good representation, or not the correct mean speed one can have here. So now how do we calculate the mean speed? So once again we use very basics here of speed, distance, time. So calculating the mean speed, we know that we just need to calculate distance. So this is the harmonic mean which we would be calculating, and we just need to calculate the ratio of the distance and the total time. Now since the total distance here is 2d, and total time we already know is d upon v1 plus d upon v2, so we can cancel out the d's here, and we are left with 2 upon 1 plus upon v1 and 1 upon v2. This is 2 v1 v2 upon v1 plus v2, and this is how we calculate the harmonic mean of any two values. So this is the true average speed for the whole journey here, and we use the harmonic mean method to calculate the same. So just like we were using geometric mean whenever we were encountering growth rates or ratios, in this particular case we use harmonic mean. So harmonic mean in this particular case is used whenever we have rates of something. So in this particular case we looked at speeds. Speed was a rate. Since speed is the ratio of distance upon time, it gives you the rate of traveling, and therefore we were able to get the correct measure of central tendency when we were using the harmonic mean. Similarly, in data sciences, harmonic mean would be used to calculate something called an F1 score. So one doesn't need to worry right now about what an F1 score is, but just to mention the application of harmonic mean, the F1 score is one of the accuracy measure for a classification model, and the F1 score is calculated as the harmonic mean of precision and recall. So PR P plus R. So both precision and recall are also accuracy metrics or performance metrics for a classification model, and we calculate the f1 square from f1 score from these two precision and recall values as the harmonic mean of the precision and recall values. So just wanted to mention one of the applications of a harmonic mean. Also, both precision and recall are rates, and therefore once again harmonic mean makes sense in this particular case. So this is about the measures of central tendency. I think this session has already become a little longer, so let's cover the measure of dispersion or measure of variation in our next session.